Organic Chemistry, Chem 213, Exam 2 Material, Part 2. Properties of alcohols, phenols, and hydrogen bonding. Properties of alcohols and phenols, and we're going to start off talking about hydrogen bonding. The structure around the oxygen of the alcohol or phenol is similar to that in water. It's sp3 hybridized. Alcohols and phenols have much higher boiling points than similar alkanes of molecular weight and alkyl halides, and that is due to the hydrogen bonding. What the textbook has in this illustration is they're showing you that the oxygen has a delta minus and the hydrogen on the same molecule has a delta plus. That's because there's a difference in electronegativity, and this is a polar bond, so we're showing the polar features of that. Hydrogen bonding happens when hydrogen is directly attached to one of three different elements, F, O, or N, and we do have it attached to the oxygen. So hydrogen bonding is when hydrogen that is attached to a highly electronegative element, such as F, O, or N, is attracted to the highly electronegative element on another molecule. The way to show hydrogen bonding is not with a solid line, as we did with covalent bonding here. What we do is we have a broken bond, and some books use them as broken lines. Other books use them as a dotted line. It's your choice on what you want to do. So this illustration is showing 1, 2, 3, 4, 5 molecules of alcohol and how they're hydrogen bonding. Continuing the properties of alcohols, common alcohols are liquids. Lower molecular weight alcohols are soluble in water, but as the R group increases, the solubility decreases. Branching tends to increase solubility over linear alcohols of the same molecular weight. The R group tends to make for decreased water solubility because they're hydrophobic, and the OH group tends to lead to increased solubility in water as it is hydrophilic. Alcohols are flammable. Lower molecular weight alcohols are more flammable and have a lower flash point than alcohols of higher molecular weight. However, all alcohols tend to be flammable. The acidity of alcohols and phenols. Alcohols are about as acidic as water. Alcohols can undergo a slight dissociation reaction with water, forming alk oxide ion and hydronium ion. So we see in here the functional group alk oxide ion. That's when you have a carbon and an oxygen with a minus sign. This is a functional group you need to know, and we are still using the same hydronium ion as we did before back in Gen Chem. Now we're going to look at the acidity and basicity of alcohols and phenols. As we noted earlier, they are weakly basic and they're also weakly acidic. Alcohols are weak Bronsted bases protonated by strong acids to yield oxonium ions. So here we have another functional group you need to learn, oxonium ion. This is when we have our carbon groups, oxygen, and 2 hydrogens attached to that, and so our oxygen is going to be positively charged. What this looks like is the lone pairs on the oxygen are going to go to the hydrogen, and this is going to cause a bond between oxygen and hydrogen. In this case, my nucleophile is going to be my alcohol. And the pair of electrons that are holding this HX together are going to be donated to this halogen, and the halogen is going to have that extra pair of electrons and have a negative charge. I want you to notice the equilibrium arrow is not equal to each other. The reverse direction is written longer than the forward direction, and what that means is it's more likely to stay in the form as written on the left than to go ahead and dissociate to the form on the right. And this is typically how we see the reaction arrows in an equilibrium when it's said that the acid or base is weak. What I've also included in this is the phenol. It undergoes the same dissociation, and here is something you may or may not have seen before. One of the accepted abbreviations for the benzene ring is capital AR, meaning aromatic, and in this case they mean that it's actually the benzene ring. Again, notice that the oxygen of the OH gets an extra hydrogen, so it's now positively charged. And then also the reaction arrows are showing us that it would rather be in the format in the beginning of this reaction than the reverse. Here we have alcohols and phenols acting as acids. The previous slide is when they were acting as bases. From this we produce hydronium ion and alk oxide ion, or in the case of our phenol, Fe oxide ion. Again, note what's going to happen here is the pair of electrons from the water is going to grab this hydrogen here and bond to it. The pair of electrons are going to go to this oxygen, causing it to have a single bond, but it does have a minus charge. I know this minus charge is kind of hard to see, so you might want to go ahead and draw that larger. And then when we have the phenol, the same thing is happening. The oxygen of the OH gets a minus charge. And again, notice, because these are weak, my reaction arrows are longer in the reverse direction is written than the forward direction, and that's because I would rather not undergo the dissociation. Only a few molecules do that. Let's dig a little bit deeper into the acidity constant, Ka. As a reminder, Ka, it's the products over the reactants. You don't include solids or water. So we have the products in brackets here, meaning concentration. Our reactions all have coefficients of 1, so we don't put any coefficients up there. It's understood that it's 1. Another thing to remind you is pKa is equal to minus the log of the Ka. Relative acidities are more conveniently presented on a logarithmic scale, which is directly proportional to the free energy of the equilibrium. The differences in pKa correspond to the differences in free energy. Compounds with a small Ka are less acidic. Table 17.1 in your textbook shows us some typical values for pKa's. The weakest acid here would be tert-butyl alcohol. What makes something an acid is its ability to give up its hydrogen, and this hydrogen does not want to go anywhere. That's what makes it a very, very weak acid. We have water a couple of places down here. And then as we move further down the scale here, we see that we have more pi bonds happening. Here we have phenol, and beneath that we have parachloro, parabromo. These are electron withdrawing groups on the opposite side of where the OH is, so the H is more likely to leave because it's not being held very tightly, and that makes it a stronger acid. Simple alcohols are about as acidic as water. The more alkyl groups you have, the weaker the acid. The more easily the alk oxide ion is solvated by water, the more its formation is energetically favored. We also have to consider steric effects. They're very important. Fe oxide ion, it's sterically accessible versus tert-butyl ion, less accessible. There's more things in the way. The inductive effects, which makes it a stronger or weak acid, remember that the inductive effects is sigma bonds. We have a sigma bond between this carbon and this carbon. I have highly electronegative fluorines, in fact 3 of them on each of these carbons here. So what that's going to do, it's going to pull the electron density away from the oxygen, allowing that hydrogen to leave to form the ion. Versus when we have CH3 groups in those same places, they're electron donating. So the electrons are going to be given into it, and so the hydrogen is more tightly held, less likely to leave. Generating alk oxides from alcohols. Alcohols are weak acids. It requires a strong base to form an alk oxide. What strong bases we could use are sodium hydride, sodium amide, or a Grignard reagent. We're going to see alk oxides a lot. They're bases, and we're going to see them in a lot of reactions in our organic chemistry. So here's some example of bases removing just the hydrogen piece of that, forming an alk oxide ion. Note that this is a negative charge, not a bond line. You might want to rewrite that to indicate that it's a minus charge, or write it down somewhere that this is a minus charge. This oxygen is still covalently bonded to this carbon, but the association between the sodium and the oxygen in this case would be an ionic bond. And we do show the charges at that point. You want a minus charge with your oxygen and a positive charge with your sodium. And the same thing is going to happen with the rest of these. Taking a look at phenol acidity, they're about 1,000,000 times more acidic than alcohols, and that's because the Fe oxide anion is resonance stabilized. Phenols are soluble in dilute aqueous sodium hydroxide and can often be separated from mixture by basic extraction. Substituted phenols can be more or less acidic than phenol itself. If you have an electron withdrawing group, especially at the para position, we saw that on that previous table, an electron withdrawing group allows the hydrogen to leave more. This is not only the inductive effect that we saw earlier, but now we also have the resonance effect helping us out there. Phenols with an electron donating substituent are less acidic because these substituents concentrate the charge. The hydrogen is less likely to leave to form the ion. Taking a look at how to make alcohols. They're derived from many types of compounds. Once we have the hydroxyl group on there, they can be converted to many other functional groups, and they are really good and useful in synthesis. Taking a look at this graphic over here, I have alcohol, and we can see that they can be converted to alkyl halides, esters, carboxylic acids, alkenes, ketones, aldehydes, and ethers. Notice that these are all reversible reactions, so we can also start off with these and form alcohols. So we're going to see a lot of reactions of making alcohols and reacting alcohols. Off to the left-hand side here, I have the nucleophilic substitution of an alkyl halide by hydroxide. We have an alkyl halide here. We're going to react it with something that has an OH group, and we can form our alcohol. In this case, the X could be bromine, chlorine, or iodine. And I have the general reaction here. I went ahead and put an R group in here using iodine, and you can see this is a substitution reaction where the iodine is being substituted for an OH. This reaction here is taking an alkyl halide and reacting it to form an alcohol. One way that we can make an alcohol is the hydration of an alkene. Hydroboration oxidation yields a syn addition non-Markovnikov product. If you'd like more details on this reaction, it is covered back in section 7.5 in your textbook. We have an alkene. This is a two-step reaction. Because this reaction is syn addition, both the H and the OH will go to the same side of the molecule. If you have a linear compound, you're not going to see the syn addition because you have free rotation around a single bond here once the compound is formed. But if this reaction were on a ring structure, you do need to show the product as syn addition. Also, the second piece of this is non-Markovnikov. Looking at the second piece of this reaction, non-Markovnikov product, H is going to go across the double bond on the side with less hydrogens, OH with more hydrogens. This is an example of demonstrating both syn addition and non-Markovnikov product. Note that the boron attaches first, and then the last step is where the OH gets attached. The previous reaction was a hydration of an alkene yielding a non-Markovnikov product. This would be the set of reagents you would use to get the Markovnikov product. Details on this is back in section 7.4 of your textbook. So we see here we have our carbon-carbon double bond, and this carbon here has one hydrogen, this has two. Hydrogen went to the side with more hydrogens, yielding a Markovnikov product. And I also have an example here on the ring. 1,2-diols, also known as glycol, can be prepared by osmonium. The hydroxylation is followed by a reduction. The product has syn stereochemistry. For more details, go ahead and look back at section 7.8 in your textbook. This is the intermediate that's happening, and this shows us why it has syn stereochemistry. The reason why we don't bring up anything about Markovnikov in this case is because the same thing is being added across the double bond. We really only talk about Markovnikov when two different things are being added across the double bond. Predict the product. Go ahead and pause the video, draw your structure, and see how you did. Because we know this has syn stereochemistry, when we have the carbon-carbon double bond on a ring and we're adding across it, you would be required to show the geometry of it. We have syn stereochemistry, so this would give us the cis form of the structure. Another reactant we can use to produce a glycol is potassium permanganate. This is still a hydroxylation reaction. You're adding two OHs across the double bond. This also has syn addition, and I wanted to show you that the middle intermediate here is very similar to the osmonium, so you can see why this also has syn addition. We've seen potassium permanganate used before with alkenes. In fact, back from 7.8 we talked about where you have a terminal alkene and an internal alkene, and we use potassium permanganate. and we didn't get a glycol out of that. In fact, this is known as a cleavage reaction. We actually cut between the carbon-carbon double bond and made two products out of it. What makes the top reaction with potassium permanganate different than the bottom one are the other conditions involved. If you have potassium permanganate under mild conditions, so that would be, for example, a low concentration of potassium permanganate, water, and cold conditions, so this would be done in an ice bath, for example, you get a 1,2-diol. If you use potassium permanganate in higher concentrations, if you use heat and also acid, what's going to happen is you'll have the cleavage reaction, and when we had the terminal alkene, what happened is it cut right here, forming CO2 and a carboxylic acid. If it was an internal alkene, the cleavage happened here, so we cut right here, and we formed two carboxylic acids. Both of these reactions are using potassium permanganate. It's the conditions that go along with the potassium permanganate that give us different products. Alcohols can be formed from the reduction of carbonyl compounds. H is shown in brackets above the reaction arrow, telling us that we're using a reducing agent, not giving us a specific one right now. The mechanism of this reaction is the hydrogen is going to bond to the carbon, the carbonyl carbon. Now this is not a normal hydrogen, this is a hydride. It is a negatively charged hydrogen being attracted to the polar positively charged carbon. The pair of electrons are going to go to the oxygen, forming our alk oxide intermediate. We're going to be seeing with carbonyl compounds this alk oxide ion intermediate a number of times. And then protonation occurs, converting the alk oxide ion to an alcohol. Note that organic reduction reactions add the equivalent of H2 to a molecule. We have two more hydrogens on there than we did before. Reduction of carbyl compounds will form alcohols. If you start off with an aldehyde, you'll produce a primary alcohol. Ketones produce secondary alcohols, and carboxylic acid or esters produce primary alcohols. The reducing agent that you can use for these reactions to reduce an aldehyde or ketone can either be the milder sodium borohydrate or the stronger lithium aluminum hydride. Carboxylic acids have to use only the strong agent of lithium aluminum hydride. When we look at reduction of esters, you don't just get a primary alcohol, though, out of an ester. We're going to see later on that you actually get both a tertiary alcohol and a primary alcohol. What carbonyl compound would you use to obtain the following? A hint on doing this is to look at the alcohol that's being produced, classify it as primary, secondary, or tertiary, and then you can predict what kind of compound you'd need for that. Go ahead and fill in this slide and pause the video, come back and see how you did. Notice in all of these cases, whatever carbon had the OH becomes a carbonyl compound, regardless if it is a secondary alcohol being formed or a primary alcohol. Wherever the OH was, that oxygen becomes a carbonyl compound. Alcohols from the reaction of carbonyl compounds with Grignard reagents. We can use alkyl, aryl, and vinyl halides to react with magnesium in ether or THF to generate Grignard reagents. Grignard reagents react with the carbonyl compounds to yield alcohols. This is the same Grignard reaction to form the Grignard reagent that you've seen before. The R groups that work best are primary, secondary, tertiary, alkyl, aryl, or vinyl. We'll be seeing in a future slide what R groups don't work that can't make Grignard reagents. Our carbonyl compound is going to get more carbons on it from the Grignard. It's the R group in your Grignard that's going to be attached to this carbonyl compound, and the carbonyl oxygen is going to be converted to an alcohol. So how this happens is the R group that's in the Grignard reagent is a carbanion with a negative charge. It's going to be attracted to the polar carbon that is slightly positively charged. The pair of electrons that was part of the carbonyl double bond will be given to the oxygen, will form the alk oxide ion. Here I'm not showing the lone pairs, but if you'd like to go ahead and put in your lone pairs here, you go ahead and do that. And then second step is this alk oxide is going to go ahead and be protonated, forming our alcohol. So the end result is the R group is now connected to the original carbonyl compound. It's now sp3 hybridized instead of sp2 hybridized. Using the Grignard reagent, if you want a primary alcohol, your starting carbonyl group can only be formaldehyde, specifically formaldehyde. If a primary alcohol of, let's say, 10 carbons was being formed, only one carbon can come from the carbonyl group, and the other 9 carbons have to come from the Grignard reagent. Primary alcohols can only be formed from formaldehyde. Secondary alcohols are formed from all other aldehydes. Ketones form tertiary alcohols, and an ester is broken up into a tertiary alcohol and a primary alcohol. Examples of our Grignard reaction with a carbonyl compound. This is formaldehyde. We know from the previous slide that formaldehyde will form primary alcohols. We have 1 carbon from our formaldehyde, 1 from our Grignard. We'll have a total of 2 carbons in our primary alcohol. It's not necessary for you to go ahead and explicitly show these hydrogens in this sp3 format. You can go ahead and write the condensed structural formula. What I wanted to illustrate in this is that it goes from sp2 to sp3, so you can also see that, visually see that, but you don't need to write them in this format. You're definitely okay to write the condensed structural formula. Here's an example of an aldehyde other than formaldehyde. That would make a secondary alcohol. This carbonyl carbon is where the R group is going to be attached. It has a total of 1, 2, 3 carbons, so we'll get 3 more carbons on here. We already have 2. We have 1, 2, 3, 4, 5. It's a secondary carbon. In fact, the name of this compound is 2-pentanol. Ketones, when they react with Grignard, we get a tertiary alcohol. We started off with 3 carbons in our carbonyl compound, 2 more here, so we have a total of 5. 1, 2, 3, 4, and then we also have our CH3 here. This is an example of a tertiary alcohol being formed by a ketone. When an ester reacts with a Grignard reagent, there's a couple of things that are different than when we had the other carbonyl compounds. In an ester, what's going to happen is we're going to have this bond right here breaking, and this section over here on our ester is going to become the primary alcohol that we talked about before. The carbonyl group here is going to have the Grignard carbon attached to the carbonyl group, but it doesn't happen just once, as we've seen before. It actually happens twice. So it's important that you note that there needs to be 2 moles of Grignard for every 1 mole of ester. What happens is this R group here that's on our Grignard is actually going to bond twice. 2 groups are going to bond to the carbon, and you can see here we have a tertiary alcohol formed from the carbonyl carbon. The limitations for a Grignard reagent is a Grignard reagent can't be prepared from reagents containing other reactive functional groups. I have some of those listed here, CHO, C triple bond N, and NO2, or from compounds with acidic hydrogens. Those hydrogens would go away before the reaction can happen, and groups that represent that would be OH, NH, SH, and carboxylic acid. Using the Grignard reagent, prepare 3-pentanol from propanal. All right off the bat here, I do see something. Okay, I know your textbook has not taught you how to name aldehydes yet, but they act like you know how to. So I do need to give you a brief preview on how to name aldehydes. If you note that when we have an alcohol, the ending is OL. That's when it's an alcohol. When it's an aldehyde, the ending becomes AL from aldehyde. In an aldehyde, I have it drawn pretty crudely over here, but you can see this. An aldehyde has a hydrogen, an acyl hydrogen, and it has an R group. And this R group could be a hydrogen or it could be a carbon group. When we name aldehydes, the carbon on the aldehyde is always carbon number 1. Because it's always carbon number 1, it's similar to when we have something on a ring, you don't include it in the name. So let's take a look at the name propanal again. Notice prop is in here, AN meaning single bonds, and then AL for the aldehyde piece. I have 3 carbons single bonded with an aldehyde functional group. This carbon of the aldehyde is counted as carbon number 1. I need 3 carbons total. So propanal would have 3 carbons total. Again, sorry for the crudeness of this. 1, 2, 3, carbon number 1, 2, 3. This is the structure for propanal. If they ask you a question to prepare an alcohol from any other aldehyde, we have formaldehyde, which is the smallest. It would be 1 carbon, and the R group would be a hydrogen. Ethanal would have 2 carbons total, propanal 3, and so on. So that's your preview on how to name aldehydes. To prepare 3-pentanol from propanal, we need 2 new carbons. Those 2 carbons come from the Grignard, so now I know what size Grignard reagent to make. Showing the reaction of the Grignard, I have my halogen connected to 2 carbons, magnesium and ether, so typically we do write ether over the arrow. And again, what happens in our Grignard reagent is the magnesium gets right between the halogen and the carbon here. So now I have my Grignard reagent so I can proceed with the reaction. I am looking for 3-pentanol. That is a secondary alcohol, so I would be using an aldehyde. The question specifically told me it was propanal. Here's propanal, 1, 2, 3 carbons. Here's the Grignard I just showed prepared above. Ether. And we also have a second step of the reaction of the protonation with the acid H3O+. Of the 5 carbons, 3 of them came from our original propanal and 2 of them came from our Grignard. Would the same product be formed if ethanol was used instead? Well, let's take a look at the reaction. If we used ethanol, which has 2 carbons in it, I would have to have 3 of the carbons coming from the Grignard reagent. We know that aldehydes do form a secondary alcohol. But take a look at this. Instead of the oxygen, the OH, being on carbon number 3 as requested in the original question, it's actually coming off carbon number 2. The carbonyl carbon is the carbon that becomes the OH. I didn't have enough carbons in my initial aldehyde to get the OH on carbon number 3. So no, you couldn't make the same product if you used ethanol. You'd actually make 2-pentanol instead of 3-pentanol.